Welcome. I'm Carl Tape. The topic, global plate tectonics, the hotspot reference frame for plate motions. We introduced the hotspots in the data sets for global plate tectonics. We examined Hawaii as a hotspot. We now see how the hotspots can be used to measure plate motions over the time scales of millions of years. These are the global plate motions from before. The motions are shown with respect to hotspots. But we can think about plate motions relative to something else, like fixed North America, shown here in white. This choice represents a choice of reference frame for the plate motions. Back, forth, back, forth. Standing in Alaska, looking south, the Pacific plate converges toward you. This is the subduction zone here. Standing in the western US, down here, looking west, the Pacific plate moves to your right. And as we know, this San Andreas fault here, this is a right lateral strike slip fault. So this sort of reference frame and picture is consistent with our understanding of the motion along the subduction zone and, say, the Queen Charlotte Fairweather transform fault or the San Andreas fault here. This one's a little weirder, but we can represent the plate motions with respect to fixed Pacific. As we saw, the Pacific's moving pretty fast relative to the others. So if we fix the Pacific, everything's moving fast with respect to it. So you can try to convince yourself that the relative motion at the boundary of the Pacific is the same as before. At the northern margin of the Pacific, the North America plate converges toward you. That's the same as we saw before in a subduction zone. At the northeastern margin of the Pacific plate, say here or along here, the North America plate moves to your right. So standing on the white, looking toward North America, the plate's moving to the right. Again, right lateral strike slip fault, San Andreas, or the Queen Charlotte Fairweather transform. So again, here the plate motions in the hotspot reference frame. As we will see, this is the most natural choice. We introduced this earlier. Hotspots are volcanoes that lie at the end of a linear chain of volcanoes. And that is a hotspot track that points from the hotspot, the youngest volcano, towards the older past volcanoes. Hot magma upwellings beneath hotspots remain fixed relative to each other while the plates move at the surface. Therefore, these hotspot tracks can be used to infer how plates move relative to the deep Earth. There's that key point. A hotspot track points in the direction of plate motion from the youngest volcano to the oldest. And so this shows the direction of the plate motion in the hotspot reference frame. It also shows, say, the direction of Hawaii. And we'll look at some of these. So let's check out three hotspots: Hawaii on the Pacific plate, Bowie on the Pacific plate in the Gulf of Alaska, and Yellowstone on the North America plate. We saw this summary slide from the Hawaii discussion. So the Hawaiian Islands, the hotspot is Kilauea and Loihi, this submarine emerging volcano southeast of Hawaiian Island. We see the orientation of the hotspot track, and in the global plate model, as expected, we see that their directions are aligned with the island chain. We'll see later in the discussion on Alaska, we'll see more about the Bowie hotspot, but the summary slide is shown here. The Bowie hotspot is shown with this triangle here in the Gulf of Alaska. For reference, Anchorage would be right here. This is Kodiak. And within the plate model, we see also this motion approximately aligned with the hotspot track. So the youngest active volcano of the hotspot would be here, and the other seamounts were older, and they formed previously when the plate was situated over this point and has since moved to the northwest, carrying these older volcanoes with it, or seamounts. Here's the Yellowstone hotspot. It's this triangle right here, and we'll look at its direction is associated with the North America plate. So again, hotspot track points in the direction of plate motion from the youngest volcano to the oldest previous volcanoes. Here's a map from the National Park Service, very simple and very succinct with the information showing the number is the age of the volcanic rock material associated with an eruption from millions of years ago. So 16 million years ago, 15, 16, 14, 12, 11, all the way up here where the last eruption was some 600 or so thousand years ago. This shows Yellowstone National Park, the dark green park boundary. And this would be the Yellowstone hotspot. The sketch also shows North America plate movement with respect to the hotspots as implied here. And we see very nicely this sequential getting older line of volcanic centers. These are not seamounts on the bottom of the sea. This isn't the Hawaiian Islands, but it's really cool to relate the Hawaiian Islands to Yellowstone and say, oh yeah, the Kilauea is kind of right here. It may not be erupting as a volcano in Yellowstone, but geologically, that's exactly what we would expect, that eventually there is going to be an eruption here. This shows another look at the same thing. And this is showing a little harder to see the states, but here's Montana, here's Wyoming, here's Utah, Idaho, Nevada, and you can see these circled sections, but you also see really nicely the topography and the bathymetry as well. And this shows the 631,000 year ago is the age of this last eruption here. And then 1.3, 2.1 million years ago. And this shows the direction of North America plate motion, again, with respect to the hotspots. So the track points in the direction from the youngest to the oldest, and that is also the plate motion. So if we extract our little piece from our global velocity model or plate motion model, we see that these arrows they're small. So North America is not moving very much, as we saw earlier, but it's moving approximately to the southwest. So as the North America plate moves to the southwest, the hotspot track extends to the northeast. So this little line of volcanic centers is moving to the northeast, so we expect it in the future it'd be heading into Montana. So eventually that national park boundary, they might as well start their expansion, because all the interesting stuff associated with this volcanism, what makes it Yellowstone, geothermal activity, is associated with the active volcanism. In essence, Yellowstone would have sort of marched its way along, and right now it's sitting with all that activity and interest here. So it appears that the volcanic field is migrating to the northeast, you could say, from that perspective, from southeast Oregon into Idaho, then northwest Wyoming. But it's better to think that the volcano-making hotspot is fixed and the Pacific plate is moving over it. That's a better perspective. Still gives rise to what we see today, but it's sort of a matter of reference. So again, we have our three hotspots. points in the direction of plate motion from youngest volcano to oldest. Two of these are on the Pacific plate, and this one's on the North America plate. See those here, roughly aligned here with the arrows from the model. Hotspot tracks aligned with the global plate motion model. So 3 hotspots of interest to us are Hawaii on the Pacific plate, Bowie on the Pacific plate, which we'll see more later, and Yellowstone on the North America plate. A hotspot track is a line of volcanoes formed as the overlying plate moves over a hotspot. The youngest volcano sits on top of the hotspot. A hotspot track points in the direction of plate motion from youngest volcano to the oldest. Plate motions can be described with respect to the fixed hotspots. This is called the hotspot reference frame and is arguably the most natural choice to display plate motion.